Okay, looks like we're recording. Hello, everybody. Welcome to VSPG. Today we have a presentation by Dr. Martin Homann titled The Barberton Greenstone Belt, a unique window into Paleoarchean life. Next week, we get to hear from Sally Pearson, and I will send out the announcement for Sally tomorrow. Sorry, Sally with Geologic Survey of Canada. So with that, I'm going to go ahead and I'm going to introduce Martin for us. So Martin Homann is a field geologist combining field-generated data with lab-based observations and geochemical analysis to pursue his interests related to sedimentology, earth history, geobiology, and the origin and evolution of life on Earth and beyond. Martin received his master's in geology, petrology, and remote sensing at the University of Potsdam in Germany, and his PhD from Freie University of Berlin, studying the Ga Moodies Group microbial mats and stromatolites, the Barberton Greenstone Belt in South Africa. And he'll hear plenty more about that today, I'm sure. He then earned the Marie Curie postdoctoral research award to support his research at the University of Western Brittany. And in 2019, he started his assistant professorship appointment at University College London. And he is PI on a collaborative ICDP grant to study the Barberton Archean surface environments of the Moodies Group. So thanks a lot for being here, Martin. We're glad to have you, and please go ahead and take it away.
Excellent. Yeah, thank you so much, Alex, for the introduction. And I'm really pleased to be here and to be part of this unique seminar series. So as Alex already mentioned, I would really like to talk a bit more about this unique record of early Archean life from the Barberton Greenstone Belt. So let's start to have a look a bit about or at some early life in the geological rock record. Just a little refresher. We know, of course, the oldest morphological evidence for life are stromatolites. The oldest or best documented examples are 3.5 billion years in age, and they are coming from the Pilbara Craton in Australia. Even older putative stromatolites have been reported from Greenland in highly alterated and metamorphosed metasedimentary rocks. Their biogenicity is still under debate. Albert and colleagues kind of questioned that these structures are actually biogenic. They suggested they might be just related to deformation and secondary alteration. And then, of course, 3.2 billion years ago, we have the first or really nice examples of siliciclastic microbial mats that I and others have studied in great detail, and you will hear a lot about them later today. The oldest cyanobacteria fossils, however, only are known from cherts that have an age of 2.1 billion years. And only at the beginning of the Phanerozoic, we had the first more complex multicellular life. And this little graph shows you actually nicely that before the 3 billion years before the beginning of the Phanerozoic, our planet was actually dominated by microbes. And it was a microbial world or a gigantic mat world, which is pretty cool if you think about it. Of course, we all know around 2.5 billion years ago, we had the GOE, the first major rise in atmospheric oxygen, the Great Oxidation Event. However, there are more and more evidence, geochemical evidence for certain whiffs of oxygen prior to the GOE, and they are often related or associated with primary producer stromatolites or microbial mats that were already capable of performing oxygenic photosynthesis and releasing oxygen as a metabolic byproduct. And people believe that around these ecosystems, probably even at 3 billion years ago or even earlier, you had certain or little isolated oxygen oases. And that's why it's so interesting to study these rocks, basically also to search for the oldest or some of the oldest evidence for cyanobacteria and oxygen in the rock record. Why do we still know so little about the early Earth? Well, you all know that very well. There are not so many places left on Earth that we can study these Archean cratons. The best places to study not metamorphosed or heavy alterated sediments are actually in the Pilbara Craton of Australia and in the Carbonaceous Craton of Southern Africa. And here's just a little summary about like the simplified stratigraphy. The main kind of biosignatures you can find in these cratons are microbial mats, stromatolites, and of course microfossils. I will talk completely about the Barberton Greenstone Belt today, where I've done most of my work so far. So the Barberton Greenstone Belt is located in the northeastern part of Southern Africa. It comprises rocks that have an age of 3.5 to 3.2 billion years. And it is subdivided in the underlying Onverwacht Group. These are mostly volcanic and ultramafic rocks, which is overlain by the Fig Tree Group, that is mainly volcanoclastic rocks. And on top, in these yellow colors that you see on this geological map, this is the Moodies Group. These are sandstones and conglomerates. The Barberton Greenstone Belt is just an amazing place to work. It has been also subscribed in the, or is part now of, actually a Geo-Heritage Site and has been subscribed in 2018. So we can still work there, but it's just protected. So nobody can come and build like a hotel, for example, on these beautiful outcrops. So it will be protected for future generations of geologists to study. It is just an amazing scenery. Outcrops are really nicely preserved. You can trace them for kilometers along strike. This is an example from the Saddleback syncline. These are steeply dipping sedimentary rock packages that are overturned. And you can imagine that it's really nice to take and measure a stratigraphic profile, which I've done in great detail during my PhD thesis, actually. The person who introduced me to the Greenstone Belt itself was my former PhD advisor, Christoph Heubeck from Berlin, now in Jena. He was really the one that ignited my love and fire and passion for the Greenstone Belt and also early life. We often overlapped in the field with Dawn Lowe and Gary Byerly and their students. Dawn and Gary are some sort of almost the godfathers of the geology in the Barberton Greenstone Belt. They have published multiple or dozens of papers and also produced an outstanding geological map of the Greenstone Belt. After my PhD, I continued my research in, as Alex already mentioned, in France, working with Stéphane Lalande and Pierre Saint-Joffre, and focusing more on the geochemistry and carbon and nitrogen isotopes of certain biogenic structures that are preserved in these unique rock formations. And this brings me already to this overview. There's a lot of information on this slide. I do apologize, but I want to give you just a general overview about the evidence for early life that we have in the Greenstone Belt. In the oldest rock units that belong to the Onverwacht Group, traces of early life are primarily concentrated in carbonaceous and organic matter-rich cherts. The oldest signs for life to date have been reported from the middle marker chert that is 3.4 billion years in age. People have interpreted these carbonaceous laminations as fossilized microbial mats. Microbial mats also are quite abundant in the Buckreef chert that probably most of you know about, and also contains some nice microfossils. And overlying units also contain beautiful preserved microbial mats and also a few stromatolites that I will talk about in a second. North of the Enyoka Fault that separates the Greenstone Belt into a northern and southern facies. Onverwacht and Group outcrops are quite rare. Most of the outcrops there are dominated by sandstones that belong to the 3.2 billion year old Moodies Group, which is preserved in isolated and fault-bound synclines. And in these Moodies sediments that I've studied in great detail, there are a lot and abundant fossilized microbial mats and also a few isolated microfossils. So in the first, let's say, third of my talk, I will talk a bit more about evidence of microbial life in Onverwacht cherts. And in the second part, I will focus more on the Moodies Group. So let's have a closer look to some selected outcrops from the Onverwacht Group. We are looking now at the Kronberg Formation. At the base, there is the so-called Buckreef chert. The Buckreef chert is about 3.4 billion years in age. It's quite a remarkable unit because it's like a chert unit that it's between 250 and 400 meters thick, and it's exposed for nearly 50 kilometers. It can be traced for nearly 50 kilometers along strike. It mostly consists of black and white banded chert. At the base of the Buckreef chert, you also have some really nicely preserved silicified evaporites. So basically, the idea is that you are in a kind of deepening upward sequence, and organic matter gets less and less abundant the deeper you go in the water column. Here are some image thin section micro photographs of silicified microbial mats that have been interpreted as being photosynthetic microbial mats. They have been studied in great detail by Mike Tice during his PhD thesis. You see these kind of streaky microbial biofilms and laminations here, for example, how they kind of drape this carbonaceous grain. And the preservation and detail is just outstanding. Also very common, you find in these cherts eroded and rolled up mat fragments that indicate a former cohesive consistency of these microbial mats, and also they serve as additional indicator for their actual syngenetic origin and support their biogenicity. Other traces of early life in these cherts are microfossils, of course. There have been some really interesting findings of these lenticular microfossils. Actually, the first publication ever that was focused on early life in the Barberton Greenstone Belt was done by Hans Pflug in 1966. He was a German paleontologist, and he already back then described these kind of spindle-shaped microfossils and other filamentous microstructures and also microbial mats. And later on, these spindle-shaped or lenticular microfossils have also been described by Maud Walsh and Oehler et al. Interestingly, they can also be found in coeval chert layers or horizons in the Pilbara Craton. There, they have been studied in great detail by Kenshio Sugitani. I think it's still not completely understood what they actually are, what their mode of operation was. Some people think they might be planktonic microorganisms, but this is still a bit under debate. Very rarely, you can also find filamentous microstructures or microfossils in these cherts. Here are a few examples that Maud Walsh has published about. So now I would like to move slightly up in the stratigraphy. We are now looking at the Mendon Formation, which is about 3.3 billion years in age. This is actually the only or one of the few places in the Greenstone Belt where stromatolites have been reported. And there's a famous paper of Byerly et al. And from 1986, a Nature paper that described these domal to pseudocolumnar microstructures that are overgrown, reworked volcanic and ultramafic deposits. And interestingly, their organic lamination often contains idiomorphic tourmaline minerals. And also quite often you can see, for example, here you see eroded fragments of these putative stromatolites that can in places also form some sort of chert chip conglomerates. So that's a kind of like indicator that these structures are actually syngenetic and at one point got reworked and redeposited. I was always kind of intrigued by these stromatolites because they are so rare compared to other greenstone belts. They only form maximum thickness of 1 to 20 centimeters, these horizons, and they occur within a 5 meter thick chert layer, the M2C chert, so the second chert of the Mendon Formation. Scattered outcrops have been reported and can be traced for about 10 kilometers along strike. And this is one of these few isolated outcrops that I've visited myself, only a few meters thick. This is basically top-down view on a stromatolite. You see this typical cauliflower-shaped weathering in cross-section. You see some dark wrinkly laminations, and in places you can also see already in the field some kind of domal structures. If you have a closer look on a surface like this, you can see again these typical cauliflower-shaped structures. This is how domal stromatolites usually weather out, and it's at least a structural indicator for stromatolite. Here another field picture. You see these underlying greenish volcanic rocks that are directly overgrown by these stromatolitic laminations. These form like little domes and pseudocolumns. But as you can see, this is only a very small or very thin horizon. Actually, their morphology is better visible, of course, if you have a polished rock sample. Like these ones, you see like domal and pseudocolumnar growth morphologies. In these thin section photomicrographs, you see that the dark organic laminations are kind of overgrown in places, or not in places, in most places, by magnesium, boron, and chromium-rich tourmaline minerals. They're idiomorphic in shape, so they probably formed very early or syngenetic with the stromatolite growth. And Byerly and Palmer, they suggested that tourmaline mineralization was likely driven by boron-rich hydrothermal fluids, or alternatively, Lowe and Byerly also suggest that the mineralization might be due or linked to a huge meteor or asteroid impact that deposited a spheral layer S8 in the Greenstone Belt. And these stromatolites are often very closely associated with these spheral layers, so there might be a link in that. However, not all the stromatolitic laminations are completely replaced or overgrown by tourmaline. In this place, yes, you see how these tourmaline minerals really line out the organic laminations, but not in all the cases this happens. So this is actually a good sign that these structures might indeed be of organic origin. And this is also supported by new organic carbon isotope data that have been generated from 16 samples. These delta 13C org values range between -34 and -22 per mil, which is consistent with a biogenic origin. I also had a master's student, Alice Hawkins, was working on these stromatolites last year during her master thesis, and she, together with Dominique Papineau, did also some Raman spectroscopy on these dark laminations, and indeed they were able to confirm the presence of mature carbon. So kerogen is, after all, preserved in these laminations, and they also estimated the T peak, or the maximum temperature that the carbon has seen at 440 degrees Celsius, which is in the range of the metamorphic degree of the host rock. So all in all, these additional data seem to support the biogenic origin of the Mendon stromatolites. Now I would like to talk a bit more about the Moodies Group. As I've mentioned before, the Moodies Group is the overlying, or the youngest group of the Greenstone Belt with an age of 3.2 billion years. It consists mostly of medium to coarse grained sandstones and conglomerates. It's about 3 kilometers thick and was once deposited in continental to shallow marine environments. It contains locally abundant fossilized microbial mats that you will hear about in a second. This is like a standard stratigraphic column from the Saddleback syncline, which is about 3 kilometers in thickness. Indicated in green colors here are horizons that contain fossilized microbial mats. So basically in the first kilometer, we have quite abundant microbial mats, and they always occur in tidal or intertidal paleo environments. They are not preserved in subtidal settings, but are very well preserved and have the highest, morphological thickness in upper to supertidal settings. These are a few outcrop images from the Saddleback syncline. It's just, as I've mentioned before, just an amazing place to work. All these rock strata can be followed for 10 to 15 kilometers along strike, and I've constructed lots and lots of stratigraphic profiles to see actually how or if there's a lateral facies change and in which environments these mats were once thriving. Here a few more images from these intertidal sandstones of the Moodies Group. You see really nice ripple planes. They of course have different directions, so I measured a lot of paleo flow directions, and of course these are quite comparable to modern tidally influenced sand ripples, because we sometimes of course like to compare the rocks and the microbial lights with modern analogs. Desiccation cracks are also quite common features in the Moodies Group. Of course, we are like in a very shallow marine paleo environment, and desiccation cracks are evidence for periods of subbarrel exposure. Modern analogs are, of course, everybody knows how mud cracks look like. For us in the Archean, these are very important sedimentological structures, because it's often like very hard to estimate the paleo water depth. So here we know at one point the water was gone, it had been dried out, and these horizons were actually exposed to the former atmosphere, which is important to estimate paleo water depth. And of course, when we find like a huge mud crack plate like this, we have to celebrate, and we like to take a group picture. Other sedimentary structures are herringbone crossbedding, which is a typical sedimentary structure that forms in intertidal settings where you have two prevailing current directions. Ripples, of course, in cross section, and little erosional channels that formed in more fluvial dominated environments. Of course, here are the fossilized microbial mats in outcrop. So all these dark winkly, crinkly nominations are fossil, or we interpret as fossil microbial mats that are interbedded with a medium to coarse grained sandstone. They definitely form a primary micro relief that is quite clear in outcrop. For example, this is a sand ripple, almost symmetric sand ripple, that is completely undeformed. So and underlying is a fossilized microbial mat horizon. So the idea is if sedimentary structures are not deformed, so why should these structures be the result of any sort of deformational features? That just doesn't make sense to me. Really nicely, we can actually see the fossilized remnants of these mats if you take like larger rock slabs and we polish them. So once again, all these wrinkly laminations are fossilized biofilms and microbial mats that sometimes were also draping little faucets or little sand ripples, sometimes form little domal structures like you can see here. And they are also in some places underlain by bedding parallel chert lenses that I will come back and talk about in a second. This is basically an overview about all the stratigraphic logs and the correlation between these logs that I've done. It contains a lot of information and it's way too small to see all this information, but the take-home message is that in the Saddleback syncline, these fossilized horizons with microbial mats, they can be found within a stratigraphic package that is about 1 kilometer thick, and it can be traced for 15 kilometers along strike. So it's really a huge area where these mats have been preserved. They are constrained to intertidal and coastal floodplain environments and also inter to supratidal settings. However, they are absent in subtidal paleo environments. And so they have a kind of fascians, they are dependent on the depositional fascias and they were once thriving. And this is also nicely reflected in their morphology. So these microbial mats tend to have more complex, tufted, microstructures or tufted growth morphologies in the most protected and most calm paleo environments, whereas if you increase hydrodynamic energy and you like in a coastal floodplain or fluvial environments, there are no little domes anymore. These mats are actually flat and they don't show like a topographic relief. And you can imagine these kind of currents, they must have been at least strong enough to transport these little pebbles. So it was just too strong. And this is an indirect indicator for the biogenicity of these features because they have a morphological dependent, their morphology depends on the environment in which they were thriving. So here in this slide, I would like to show you more information about these bedding parallel chert lenses that I've just mentioned before. And they always occur underneath fossilized microbial mats. And our interpretation is that these might have been once filled by air, or these might have been once gas-filled cavities underneath cohesive and impermeable microbial mats. This is actually a quite common feature that you can often observe also in modern mat environments. And these are not just like, these former cavities are not just filled, mineralized by chert. No, they also contain carbonaceous laminations, like you can see here and there. In places, you also see structures that resemble silicified gas bubbles. Often, if you have a closer look, especially on the roof of these former cavities, they are structures that seem to, they resemble microstromatolites that may have once grown into like an open air-filled space downwards. And high-resolution SEM images has even shown the presence of filamentous moles that form interconnected networks and are really preserved in 3D and deeply embedded in the chert. Often these filaments are segmented into 2 micrometer thick segments. All in all, this shows that also cavities that were formed underneath cohesive and impermeable microbial mats were inhabited by filamentous microbial communities. We have performed some Raman analysis on these dark laminations within the cavities, and these has has confirmed the kerogenous composition of these lamination and also the syngenetic origin of the kerogen, because it has the typical, the D and G peaks show like a typical peaks shapes that we expect from green schist facies metamorphism. And green schist facies is also the metamorphic degree of the surrounding host rock. Thus, it supports the biogenicity of these laminations. Of course, it is also always very tempting to compare fossilized microbial mats with modern analogs, which I've done in this figure. On the right-hand side, you see modern cyanobacteria dominated microbial mats from Tunisia. And on the left side, these are examples from the 3.2 billion euro Moodies Group. And yeah, what can I say? It looks very, very similar. Mat fragments are also very common. Eroded mat fragments are very common in the sandstones of the Moodies Group. And roll-up structures are also common features in modern mat environments. Modern mats often also show these kind of tufted morphologies. These are formed to my knowledge, exclusively nowadays by filamentous cyanobacteria, and often in these former or in these tufts, you can accumulate gases. In this case, oxygen, and similar structures, similar tufted micromorphologies have also been identified in the Moodies mats. And some of these tufts also have a hollow core that is now filled with chert. Of course, I would love to know if there was once oxygen in these bubbles, but yeah, it's impossible. It's impossible to tell. Also, larger accumulations of gas beneath microbial mats have been preserved in the Moodies Group. These cavities are also now, of course, filled with chert. And it's just another nice morphological similarity to modern mat environments where gas domes are actually quite common. So far, I've only talked about Archean or Paleoarchean life in shallow marine paleo environments. So now I wonder, what are the evidence for terrestrial life in the Archean? So life on the first exposed continental landmasses. So the evidence are actually not that many. So we have putative biosignatures at 3.48 billion year old hot spring deposits from Australia. Jokic et al. Published about this in 2017. This is an image from their publication. Here, the authors have interpreted these structures as fossilized gas bubbles, and they conclude that these structures can only be preserved in the presence of sticky EPS, and so that's like an indirect indicator for the former presence of microbial life on the continents in these hot spring deposits. Geochemical signs in paleosols indicate biogenic fractionation of sulfur already at 3.2 billion years. This is a study by Napan et al. From 2016. However, the only real direct fossil evidence for life on land, let's say, are only 2.7 billion year old fluvial lacustrine stromatolites from, I think, the Pongola formation in South Africa and the Tumbiana formation in Australia. So there's actually not so much direct fossil evidence for life on land. And this brings me to the diastole syncline. So the diastole syncline is a small isolated syncline, fault-bound isolated syncline of the Moodies Group. And it's interesting because it's there was a paper in 2006 by Erickson et al. Who reported about an unusual fluvial to tidal transition in the diastole syncline. So it's actually the perfect place to look for signs of life or fossil signs of life in fluvial deposits in the Paleoarchean. And this is what we did. So we produced a really nice updated geological map of the syncline and a high-resolution stratigraphic column, which basically at the base, we are like still in fluvial terrestrial environments, and That's like a deepening upward succession. We end up in marine or in subtidal deposits. So we're going from braid plane deposits into upper and lower intertidal, and finally in subtidal deposits. And at the very basal part, in the fluvial dominated environments or paleo environments with lots of conglomerates, we also have identified a few horizons that actually contain microbial mats. And here they are. That's a nice outcrop view of this microbial mat laminated horizon that you see here, interbedded with really poorly sorted, pebbly, conglomeratic sandstones. Another outcrop image shows again these conglomerate layers, microbial mat horizons, another conglomerate coming in and is directly overlain and interbedded with microbial mats. These mats were directly draping these pebbly conglomerates. These are polymiced, poorly sorted conglomerates. And they're not just pebble size, but also sometimes fist-sized clasts are directly interbedded with the mats and overgrown. So this was really an episodic, at least episodic, very high energetic and paleo environment in which these mats were thriving. Other quite interesting observations are these structures here. That's a close-up. These are fluid escape structures. You can imagine that a microbial mat contains about or even more than 90% water at one point. This water with overlying sedimentary layers, this water has to escape and kind of migrates upwards and plastically deforms the still unconsolidated microbial mats, which is another nice, structural or morphological, how you say, this supports again the biogenic and syngenetic origin of these mats. In polished hand sample, the microbial mat layers are really nicely preserved, often form very thick horizons or laminations. They overgrow and stabilize former ripples. Mat fragments are also quite common. And of course, it's, as you can see, it's really poorly sorted, pebbly, coarse-grained sandstone. In thin section, we can even see these microbial mat horizons, and in places you can also identify fossilized potential filamentous microfossils that in this place have been partially eroded by heavy minerals impacting this former mat horizon. Mat fragments are also quite common features that you see in the outcrop and also in thin sections. Here you see little sand grains impacting the mats and slowly peeling off little mat fragments, and little erosional channels are also downcutting and partially eroding these carbonaceous laminations. Also here we performed some Raman analysis together with colleagues from IPGP in Paris, and once again the carbonaceous composition of these lamination has been confirmed. So we have mature kerogen preserved in these laminations. This lamina, or the peak temperatures that the carbon has experienced, was about 365 degrees Celsius, which is also the metamorphic degree of the Moodies group. So it supports the syngenetic origin of the organic carbon. Here another thin section image. This is like an entire thin section scan, which I just show you just to highlight the detail of preservation. So all these like dark horizons are former microbial mat horizons. You see a clear difference also in grain size and grain size distribution. And that's a close-up of the box. The red area here is just highlighting again the detail of preservation that was due to the early silicification of these mats. And if you compare this with modern mats, it almost looks identical. So it's it's really exquisite preservation. Now I would like to compare the marine mats, the fossil mats from the Saddleback syncline, with the terrestrial fluvial mats from the Deister syncline. The marine beds are usually interbedded with medium to coarse grained sandstone. They show sometimes crinkly and tufted growth morphologies like this one here, whereas the fluvial or terrestrial mats are interbedded with pebbly sandstones and conglomerates, and they're mostly planar, but generally thicker mats. That is probably due to, you know, the more energetic environment in which these mats were thriving. Of course, we also performed some organic carbon isotope analysis, which shows also significant differences between the marine and the terrestrial mats. Marine mats indicated in blue here and terrestrial in green. So the terrestrial mats show a very narrow distribution of their delta 13C org values that suggests a relative homogeneous source of carbon, usually around, or mean values are usually around -21 per mil. This is consistent with the autotrophic carbon fixation via the carbon-benzyl cycle. The marine mats, however, have similar values, but they reach also more negative delta 13C org values, and some of them are as low as -34 per mil. This is best explained with carbon fixation via the Wood-Lungdahl pathway that also includes methanogen and sulfate reducers. Of course, the ultimate goal is to kind of pinpoint the metabolism of these microbial mats. And this diagram just shows the delta 13C org variations of major microorganism groups. And if I plot in the delta 13C org values that I've just shown you, we see, well, the fluvial and the marine mats, they are consistent with, you know, with values that we would expect from cyanobacteria. But as you all know, there's also huge overlap with unoxygenic photosynthetic bacteria. And I think what we can definitely exclude is that these mats were formed by methanogenic bacteria that usually form or have way more negative delta 13C org values. So it's still an ongoing debate what actually is the main metabolism of the Moodies microbial mats. And to get further insights, we also performed some nitrogen isotope analysis on these mats, on the terrestrial and marine mats. And also here we see significant differences between these two end members. The terrestrial mats show values, so nitrogen isotope values between +2 and +5, whereas the marine mats have values only around 0 and +3 per mil. In general, there are 3 different biological mechanisms that can produce biomass with nitrogen isotope values of larger than +2 per mil. The first one is partial assimilation of ammonium. The second one is partial nitrification, and the third and probably most likely one is partial denitrification. However, these last two, they require an oxygen nitrogen cycling, and as you have heard before, it's still under debate if oxygen was actually present at 3.2. So that's still ongoing research. However, the prebiotic generation of fixed nitrogen in the atmosphere through lightning discharge is an alternative way how nitrogen would have been made accessible to these microbes. So that's the research in progress, I want to say. So to briefly summarize what I have told you in these last, 43 minutes, microbial mats are the oldest and most widespread traces of early life in the Barberton Greenstone Belt, and they occur throughout the entire stratigraphy. Stromatolites, however, are surprisingly rare in the Barberton Greenstone Belt and are only known from a few isolated localities. The fluvial to shallow marine microbial mats of the Moodies Group were likely formed by filamentous photosynthetic microorganisms, and they show some striking morphological similarities with modern cyanobacterial mats. However, we don't have a direct proof of if cyanobacteria was present back then, of course. So that's still, as I said, that's the research in progress. And the outlook is that, actually, we will look more in detail at the rocks of the Moodies Group very soon, because we have an ICDP drilling project called BASE. This is a picture from our first, or that was a pre-drilling workshop in 2017, hosted in South Africa. The money was funded by the ICDP in 2019, I believe. And we started actually drilling from November 2021 to June 2022. A total 8 cores of Moodies, sandstones and conglomerates and Bennett iron formations were drilled from 5 sites, and we have a total drill core length of about 3 kilometers in thickness. There are 9 PIs in total, and of course I should mention Christoph is the lead PI and the initiator and driving force of the ICDP drilling project. These are a few images from the drilling operations that was in the white outcrops, where we have, which is in the Dystare syncline. And we also see here in the drill course directly the fossilized microbial mats interbedded with these fluvial conglomeratic sandstones. So we have really now fresh and unweathered core material that will be analyzed in the future. And here a few images from the actual drilling itself, or videos. That was in the Stolzburg syncline. I was there in May 2022 to kind of observe and have a look at the drilling activities, and we were the first to actually put our hands on these unique drill cores. So there's more science to come in the future. Then these cores were described first in Barberton, cut in half. One half will stay as the archive half, is staying in South Africa. The other one was shipped to Germany actually, and is currently XRF core scanned by a team led by Stefan Lalonde and Paul Mason. And in September 2023, we have our core sampling party. And as you have seen, there's so much material that will really keep us busy for, I guess, the next decade. And we hope to find more interesting observations in these unique drill cores. So stay tuned. And with no further ado, I would like to thank all my collaborators over the years, and of course also you for your attention. And I'm more than happy to take any questions. Thank you.
Thanks, Martin. Really great. So for everybody, we're going to transition to question and discussion. Martin, as you may know, we don't really stop that at any point. So if you need to go, just let me know and I'll cut it.
Sure.
So you can ask in a couple of ways. You can type in the chat and I can ask it for you, or you can locate the raise hand button. Go find the bar at the bottom, go to reactions and click that. It's at the very bottom of reactions is the raise hand. I have one in the chat that came into me during the talk, so I'm going to ask that first, and then Francis, you'll be up next. So Karthik Sundar Sarwan asks, are there any bioherm-like structures observed with these stromatolites, or are these stromatolites solely solitary?
Right, let's have a quick, let's go back here to the stromatolites. Well, that's like just a question of definition. I would say these kind of stromatolitic horizon, they might form like small bioherms. Yeah, I would say they form small bioherms, but they are they're not very thick. So I don't know if that answers your question. Maybe you can unmute yourself and
Let's see.
So these are general very thin horizons.
He's gone.
All
he's
right.
not in the chat anymore. So he'll catch up on YouTube.
Okay.
Go ahead, Francis. Please unmute yourself. Thank you.
Okay. Thanks a lot for a great overview, Martin, and very interesting new work coming up. Regarding the big question, when were these microbes, photosynthetic microbes, oxygenic or not?
Yeah.
Have you done any work with the rare earth elements? Any detailed geochemistry that could give you a handle on that?
Yeah, that's a very good question. Actually, the first thing that I did when I went to during my postdoc, I don't have a figure here. I had a look at carbonates that are associated in some places with these. That's probably a good example. So that's, I've actually not mentioned that in my talk. Some microbial mats also contain some calcareous buildups, and of course that's, you know, carbonates would be like prime targets to look for, to study rare earth elements, especially in situ, and look for negative serum anomalies. And this is what I did, for example, in these carbonates. And unfortunately, there's no serum anomaly. But then it's also the question: is this a primary carbonate? These are mostly anchoritic or dolomitic in composition that may have also like alterated the, you know, the rare earth element spectrum. So rare earth elements, at least from the outcrop samples, show no negative serum anomaly, so no real indicator for the presence of oxygen. But we hope to, I mean, of course, we will continue this work also on the fresh drill core. So that's something we will look into in the future.
Great, I'm looking forward to that. Thanks a lot.
You're welcome, Francis.
Okay, next we have Greg. Please unmute yourself.
Yeah, great talk, Martin. I really enjoyed that. But now I'm going to ask you something completely unfair.
All right.
Because when I visited the site with Christoph and in Christoph's talk too, we were quite struck that maybe even some of the things you're looking at here are parts of paleosols, either gypsic or calcic horizons of paleosols.
Yeah.
So how is the paleosol side going, if at all?
Well, that's a very good question that what I'd like to direct directly to Sami, who has actually looked in great detail at these paleosols. So I can't really answer you that question because I've only looked more at the microbial mats itself. But these structures here, this is really like, I don't know if you can still see my screen. This is what we are currently working on. These might be like these might be structures that form in the subsurface, you know, these calcareous buildups or precipitates. They might be defined or classified as paleosols. I mean, you are the expert. What do you think about it?
Yeah, let me unmute. Yeah, they don't look quite right. I mean, a pedogenic nodule, even back then, should be macritic and non-laminated, not concretionary. Some of these look okay, others not so much, and they should be replacive. So some look all right and some don't, but you know, nodules growing within pre-existing microbial mat may follow the outline of it. But the key feature is there should be some sort of surface above, which would be the original soil surface, and these would be a subsurface horizon. And then they should taper off the further down you go. I don't see evidence of that, but so yeah, these are ambiguous, I think.
The thing is also that these calcareous buildups, they are always like beneath or underneath you know, former, or like at least what I interpret as former microbial mats. So there seemed to be like a direct link between the mats and these buildups. We have not seen like any kind of concretions, at least in these environments that are without the microbial mats. But of course, we hope that the analysis of the new drill course will give us like more insights also about the paleosols. We have also drilled like really paleosol horizons that have been studied by Sami and others before. So
It just occurred to me that there is a kind of a parallel to this in the Karoo, not too far from where you're studying. It's quite common for caliche nodules within calcid soils in the Karoo for the nodules to actually come out in bone and around bone and then grow around the bone. So you could be looking at a comparable phenomenon. No bone back here, of course, but where some pre-existing structure is being preferentially sought out by the carbonate.
That would make sense.
Pretty interesting, yeah. No, what I'm really waiting for is some nice, juicy chemistry on the whole profiles, and particularly in the core, because what we looked at in outcrop was, well, it was too weathered to bother with.
Exactly, yeah. That's why, I mean, that's why we need these drill cores to give us like more an unweathered insight in these deposits.
Anyway, I'm excited. Well done.
Yeah, I'm pumped too. Thank you.
All right, Hedda, go ahead, please.
Hi, thanks, Martin. I really enjoyed this talk. So I have two questions, maybe. One of them a little bit broader. So I was wondering, a lot of these fossiliferous units in the Ediacaran, they seem to be kind of stuck or focused on in the early Ediacaran or mid Ediacaran, so from 3.5 to 3, but we don't actually see a lot from sort of 3 until the Ga Mohan formation, so just before the GOE. So I'm wondering if is this simply because we just don't have lithology to see a lot of these useful rocks for organic preservation, or is it, like you were mentioning, the depositional facies for the preservation of organic matter are missing?
I would say, well, it's probably both, but we're always limited to the amount of rocks that are preserved. You know, that's why we've got these huge gaps also in the Paleoarchean and Mesoarchean rock records. So I would say it's just a preservation bias, because you look at the oldest rocks, the oldest sediments, they are full with stromatolites, or at least some in Australia. So wherever we have favorable environments for life, and also when these deposits are preserved in the Archean, there is life. So I don't know if this answers your question, but I would say the gaps are mostly due to gaps in the geological rock record.
Okay, thanks. And I just have another question,
Sure.
A really brief one. Sorry, Alex. So I was really intrigued by the way that you showed differences in the organic carbon composition of terrestrial versus marine mats. And you've shown that there's actually a very narrow distribution in the organic carbon composition of the terrestrial ones, possibly showing there are more metabolisms in the marine realm. But I'm also wondering, is it possible that there's kind of an overprint on the terrestrial record due to diagenesis? Or, I mean, we're looking at very shallow environments that would be on land. I'm imagining kind of pools and things like that, reported by Knauf. Is this due to really these environments being dominated by cyanide or some kind of anoxygenic photosynthesizers, or is it?
Yeah, very good question. So the only thing we can say that probably in these two different end member environments, we had perhaps different microbial communities, and it seems like that in the marine realm, we may have had more sulfate reducers or methanogens. But of course, there's like as you've seen before, there's a huge overlap. I'm not sure if the rocks have actually, if they have been altered more in the fluvial settings or in the marine ones, because all these rocks have been like silicified very early, and we have actually no reason to believe that the carbon isotope values have been significantly overprinted differently in these different environments.
Okay, great.
Thank you.
Thanks. Eva, please go ahead.
Hi, Martin. Thanks for your talks. Really cool photos. So I was curious, you showed these really intriguing similarities between the ancient mats and the modern ones.
Yeah.
So does it also mean they were maybe growing at the same rate? And would that tell us something about nutrient availability, perhaps?
Yeah, well, let me just show that image. Yeah, well, that's always the question. I mean, we know that modern cyanobacteria mats, they grow very quick. They can produce their biomass very quickly if the conditions are favorable. We have actually no real handle on how much time is in these, in these rocks. How much time did it take to form this or that mat layer? We know that sediment or the sandstones, they are deposited very quick, but probably these mats still needed a certain time to grow. And nutrients must have been, it seems like, available quite abundant. Of course, we've got these huge, we've got volcanoes weathering in the back and in the hinterland. So there will be plenty of ultramafic rocks weathering, so plenty of nutrients. So I think the conditions were very favorable for microbial grow and microbial mat grow specifically. whenever the conditions were right, sedimentation rate was not too high, at least in the Moodies Group, it seems like life was just going crazy, and these mats were growing and stabilizing the sediment before being buried again. So I think maybe they had like similar growth rates comparable to modern cyanobacteria mats, but once again we don't have a direct proof for the presence of cyanobacteria at 3.2. So that's the work in progress. But I guess also other photosynthetic non-oxygenic bacteria can grow quite quickly and can also form quite resistant filamentous microbial mats. I hope this answers the question, Eva.
Yeah, thanks a lot. Yeah.
Okay, Martin, I wanted to actually talk with you about the bubbles you find in these.
Yeah.
So your carbon isotope nitrogen isotope diagram is really great. It shows there's definitely a couple different communities going on here. But I guess maybe I don't know how much detail you've looked at the bubbles, but do you find bubbles in both in both of these environments, number one? And then I guess number two is, do you usually see these bubbles with similar morphologies, or are they clustered near the tops of stromatolite columns? How are they spatially and morphologically similar or different?
Yeah, so very good question. So they tend to accrue in similar kind of facies. Usually I found them often in the most shallowest parts, at least in the saddleback syncline, so in the upper intertidal to supratidal settings, where you can imagine that productivity was probably also like higher. So this is where I see higher abundance of these tuft-shaped microbial mats that have also these hollow cores or gas domes. This is similar to the terrestrial and the marine mats. So also in the fluvial settings that were like by default very shallow, we see pockets that are also gas filled, or no, not gas filled now, but we also see gas domes. However, these pockets are often still consist of carbonate. But I guess this is just like a preservational feature that in these particular rocks of the diastole syncline, maybe the rocks are generally better preserved. And we hope to find out more once again when we have a closer look at the drill cores that are not really prone to like superficial or surface weathering. So there's a facies dependency of these tufts and gas-filled pockets. So they don't occur throughout the stratigraphy. They are really in the environments that I consider were once most productive or bioproductive.
Okay. Yeah, I guess my thoughts in general when you were mentioning that it might be impossible to really know what was inside these bubbles.
Yeah.
I've sort of, I guess, thought a bit and discussed with some colleagues that maybe if, how you're making the bubble, you might expect different morphologies. I mean, if you're producing oxygen, you're not consuming anything, you're not destructing any, but if you're creating a gas when you're consuming organic carbon, you're kind of you're being somewhat destructive, right? So I just wonder if, a detailed study of morphology of the bubbles could, and this is just so well preserved, it would really be the place to do it.
Yeah, and another, just remember now, another also like key thing is that you not just need something that is producing, oxygen or any sort of gas. You need to produce that very quickly, because these mats were like constantly like buried. So you need a mechanism that produces not oxygen, like any gas, very quickly. And then preserve the entire feature before this whole thing is getting buried and squished again. So the only metabolism to my knowledge that can produce gas very quickly is, oxygenic photosynthesis. We see this in modern environments. I don't think that, other gases can be like formed so quickly due to metabolic activities.
Okay, interesting. Okay, thank you. Does anybody else have any questions or points of discussion? I'll go ahead, Tony.
Thank you, Martin, for absolutely fascinating talk. And I'd like to come back to Ava's question a bit. Could you go back to that beautiful polished slab that you have? Because this, the big one.
The big one, yeah.
That one,
That's
yeah.
my favorite. Yeah.
Yeah, well, I can see why.
Yeah.
So this is really just a curiosity, and
Yeah.
I'm sure you probably thought about this, but if we consider, okay, tidal sandstones, we go back to 3.2, whatever the length of day was, so tidal periodicities would be less, shear stresses associated with tidal currents would be greater because of shorter days, etc. And when you look at these mats that you show there, they look like they're growing immediately and draping over what would be either one of these diurnal cycles or perhaps a spring neap cycle or even individual foresets.
Yeah.
So does that tell you something about the rate of growth?
Well, of course, it would indicate that they were growing very quickly, but of course not. You know, we don't see how you say, if this would form, if microbial mats would really form in between each tidal cycle, then perhaps the Moodies group would be like super thick. But of course, there is always an element of erosion and
Sure.
so on. But yeah, they, in my point of view, they must have been able to grow very quick in this sort of environment. And then it's the question, why are they thriving in there at all? Well, at least I mean, you know, the basic or the key assumption is always, yeah, why are they there? Probably they needed at least light as an energy source. So but yeah,
But
I think they must have been going.
It does look like a miserable place to live, all this coarse sand being washed around over the top of you, eh?
Exactly. And then think about, you know, the fluvial mats. So that's really not where you want to be if you have a choice. But perhaps they were also in different places, but this is where we have them preserved. So
okay. No, great, thank you.
You're welcome.
Okay, Daryl, you're up.
Yeah, I was very intrigued by your so-called fluvial facies there, particularly as that I can model a sheet flood on that. But what struck me is that the facies you're dealing with, all your fluvial units are exceptionally thin. Like the conglomerates underneath, I don't have a problem with those, but could you be dealing with a pro-delta slope facies rather than a true terrestrial facies?
Yes, well, of course, that's that's the way you can interpret that also, perhaps in a different way. We basically used like previous interpretation where these especially these environments in the distal syncline were interpreted as being a fluvial in origin. Also we got this like nice deepening upward sequence from fluvial to intertidal, then to subtidal deposits. So from this context, it would make sense. Not sure about deltaic deposits because we don't have really a lot of fine-grained material associated at all with these conglomerates. So yeah, there might be different ways to interpret these rocks, and I'm sure you're like an expert in fluvial deposits, so you seem to prefer a different interpretation.
Well, I'm just a little bit cautious when it comes to these interpretations, having not seen the stuff myself.
Right.
Another aspect of your stuff, you showed some non-polygonal cracks and described them as desiccation features.
Right. Yeah.
They seem to have the outer surface of the polygons bending down rather than bending up, which is classical for a desiccation feature. Could these be seismic in origin rather than true desiccation features?
Right. Well, you mean these features?
This
here?
one, yeah.
Yeah.
This one.
Well, of course, it's a very good question. I mean, who am I to say these are definite desiccation cracks? So in places they really look like desiccation cracks. Of course, seismic events. I mean, we know that there were like huge meteorite impacts at that time. So perhaps a meteorite impact could have maybe led to the formation of like similar cracks. But to be honest, I can't really.
Is this an upper surface or a lower surface? Is it an overturned block?
That's
Or
the question.
Yeah, that's the question. Well, I can tell you this. We are looking at the other way. So that's overturned. So the hammer is lying on.
okay, that's not a problem then.
Yeah, because here there you see there's slightly bending down, but in most places they actually kind of how we would, you know, identify desiccation cracks. You know, these kind of structures.
Well,
However,
those are also very similar to syneresis cracks. So
yeah.
There's a whole world of cracks that is
I know. So the reason why in places like this we kind of interpret these features as actual desiccation crack is also we have associated herringbone cross-bedding. So we know we are very shallow from the facies type. You know, it would make sense to have desiccation cracks there that are actual desiccation cracks. However, you're right. There are also syneresis cracks that don't form due to due to evaporation. They form they're like in the water column. Yeah.
Okay, thanks a lot.
You're welcome. Hey.
Okay, great. Christoph?
Yeah, hi everyone. Great talk, Martin. Yeah. This is just a comment to Tony's comment on Moody's not being a really great place for microbial mats to develop. I would say it's close to paradise. If I was a bacteria, there was barely a better place for me to grow or to develop than a tidally dominated delta with a lot of airfall tufts providing nutrients and occasional desiccation and frequent flooding and a plethora of low to medium high energy environments and billions of pore spaces for growth and a moderate to high rate of mutation from the UV radiation. I would choose to live in a tidal delta.
You're much tougher than I am, Christoph.
Well, if I was a bacteria, and remember, we know virtually nothing about these bugs that may have been around back then, and we just wondered about the growth rates. And
yeah,
Martin mentioned, or it may have been a term invented, or which I may have first heard by Don Lowe. These may have been superbugs. We don't know about their growth rates, and other evolutionary factors may have outcompeted those super fast growing microbial films sometime later as radiation went down or became less virulent.
All right. So let's go ahead. Do you have comments on that, Martin? Sorry.
I think I fully agree with Christoph. If I would have been a microbe, this is like the place where I would have lived in the Archean. But of course, I'm biased.
Okay, so let's go ahead and just open it. If anybody wants to step in and say something here, feel free to.
So Martin, I have a
Sure.
question. So you talk about this microbial mats and below them chert develops, and you showed this mini stromatolites, but so it seems like they wouldn't be probably photosynthetic, right?
Sorry, you're talking about
yeah,
about this? Okay. Mm-hmm.
yeah. So do you have any geochemical data to consider, like if we're chemotrophs or what was their metabolism?
Yeah, I've not shown it actually here. We have performed some in situ SIMS measurements on these like carbonaceous laminations, and they have like they show like very similar values to the mats. Actually, if I remember correctly, they were between -22, 28 per mil, something like this. So not super negative. Nothing that I would consider to be the result of methanotrophs. So yeah, there is some geochemical measurements have been made, not bulk, but in situ measurements on these carbonaceous laminations within the structures that we interpret as cavities.
Yeah, it would be maybe interesting to do some sulfurizative work.
That's true. Yeah. Yeah, we should have a chat about that. I've plenty of samples.
Yeah,
Well,
cool.
cyanobacterial mats commonly have an underlayer of heterotrophic bacteria.
Yeah.
It's also interesting to note, I think, that molecular phylogeny people now are advancing the idea that oxygenic photosynthesis is more primitive, ancestral, and anoxygenic photosynthesis is later and derived.
Yeah. Yeah.
Surprising everyone, but but the former view is really nothing more than an assumption.
Yeah, is that the work of Tanay?
Yeah,
Cardona?
that's right. Tanay
Yeah.
Del Cardona
Yeah, he is.
and Patricia Sanchez Baracaldo at Bristol.
Exactly. Yeah, that's.
Yeah, Cardona is at Imperial College, I guess.
Yeah, that's right. Yeah, that's of course. I mean, there might be like some old paradigms that. So it's good that these people have a closer look from a biological and evolutionary point of view, and also they have a lot with their phylogenetic analysis. So yeah, it's very exciting stuff.
Yeah, the tufted mats certainly look a lot like modern Cydenema and Lingbia. These are very heavily pigmented.
Yeah,
for protection from UV.
Exactly, I agree, but you know, it's always so tempting just to compare morphology, as you know,
Sure.
and say, oh, this looks like this, so it's the same mechanism or the same microbe responsible, but it's so tempting.
Yeah, but there may be, cytonemin is an ancient compound, whatever it is that, who knows what you may find.
Yeah.
So how much organic matter is preserved in?
It's very low. If I remember correctly, it's just like 0.3 per mil in places, because even though these mats look quite thick, but under thin section, let's have a look. Well, best preserved examples are, for example, like this. They are, in places they are thick, but it's not always that much organic matter preserved. So yeah, TOC values are relatively low, but it's not a black shale. It's what you would expect from organic matter preserved in a sandstone.
But are those outcrop samples or drill core?
This is outcrop sample.
Yeah, so drill core may be different.
That's right. Yeah, that's right. Yeah, that's why we've got these drill cores to look in detail also at the microbial mats, the organic matter, and rare earth elements, carbon and nitrogen isotopes. Plenty of things to do.
Yeah.
Okay. Any last thoughts? All right, thanks a bunch, Martin. This was really good. Lots of good discussion too. So, and good to have you in California, and we'll have to have you visit for sure.
Definitely. Thank you so much for all the questions and for your interest.
Yeah. All right, everybody, take care, and we'll see you in future seminars.
All right. Bye.